So I will start the recording. Um, so in the last class, we we derived the expression for electron and hole concentration in the intrinsic semiconductor. So intrinsic semiconductor means so this is a pure semiconductor without any crystal defect, right? Without any defects introduced to the semiconductor, right? So we derived these expressions. So I'll just go through it quickly. So N0 is the electron concentration in the intrinsic semiconductor. This is Nc e to the minus Ec minus F by Kt. So here the Nc is the effective density of states, and Ec is the conduction band, and Ef is the Fermi level. Similarly, P0 the hole concentration, intrinsic hole concentration. So this is Nb exponential minus Ef minus Ev by Kt. So again, Nb is the effective density of states of the in the valence band, right? So we also know that effective density of states in the conduction band and effective density of states in the valence band depends on the effective mass, right? So if you multiply these two equations, N0 into P0, this will be Ni square, because so in the intrinsic semiconductor, the electron concentration is always equal to the hole concentration. So N0 P0 is Ni square, which is NcNb e to the minus Eg by Kt. So your conduction band here, Eg, is nothing but Ec minus Eb, right? So band gap is nothing but the bottom of the conduction band, the conduction band minima minus valence band maxima, right? So this is Eg band gap. So from here we could also derive that Ni, the intrinsic carrier concentration, is nothing but root over NcNb e to the power minus Eg by 2 Kt, right? So we also towards the end we discussed that your intrinsic carrier concentration will depend depend on band gap, right? So if the band gap is lower, you will have higher intrinsic carrier concentration, and vice versa. Okay, so this part we discussed in the last class. I hope everything is clear. So before going to the topics in this class, I want to discuss about EK diagram and energy band diagram. So so there is a difference, because many times students mix up with EK diagram and energy band diagram. So actually these are two different uh, diagrams, right? So they are not same, right? So EK diagram, so let's say if I take a semiconductor, right? So let's say if I have a semiconductor, right? And this is my X direction, right? And let's say this is Y direction, right? This is a semiconductor slab. So when you plot EK diagram, so energy band diagram is, so basically this is nothing but energy, right? So so this is nothing but energy and momentum. So in the Y axis we have energy, and X axis this is momentum. So energy is total energy. So and we know how does the EK diagram look like. So EK diagram will somehow look like this for okay, for silicon. So your valence band maxima and conduction band minima is not at the same K. So if this is K equal to 0 point, right? So and this is towards 100 direction, right? So this is towards X value, right? X value, right? Okay. Anyway, so this part we have discussed. So EK diagram is nothing but when we are plotting energy of electron or energy of a hole as a function of momentum, right? So this EK diagram will be same at every point in the semiconductor, wherever you put. Let's say if you want to draw the EK diagram at this point, so the EK diagram will be same, right? EK diagram in the intrinsic properties of the semiconductor, right? But when you talk about energy band diagram, so energy band diagram, when you plot E, okay. So for the energy band diagram, so we we are interested in the energy. So this is in the um, y-axis will have energy, and the x-axis it is x, right? So basically you could plot with the direction to x or y. So basically you could so energy band diagram is the energy as a function of position, right? And if you're plotting energy of electron, right? So that means, so basically we we assume that I mean assume that electrons are at the bottom of the conduction band, so mostly here. So that's the reason we take the parabolic expression at this point, right? This is the effective mass, right? So uh, then this is the energy of the electron, right? So then if you want to plot energy band diagram, then you plot the energy of the electron as a function of x, right? So if there is no external force, then your energy of the electron will be same as a function of x, right? So basically so you just take this minima, this energy here, and plot how it varies with x, right? So basically you are taking ek diagram at every point, right? And assuming the electrons are the conduction on minima, you are just plotting this energy as a function of x, and then it will look like if this, so this is look like a straight line, because this is always the bottom of the conduction band ec. So this is my energy of electron as a position of x, right? As x, right? So and similarly if you plot the whole, so then this will be ev, right? So this is the ec and ev, right? So this is the energy band diagram, right? So energy band diagram is energy as a function of position, right? So position can be x, y, g direction, x, y, z direction. But ek diagram is the energy as a function of momentum, right? ek, right? Energy and momentum. Okay. So so the so is there any question here? This part clear? So if I ask you to plot energy band diagram, so energy band diagram, you'll just plot EC, EV. This is my energy band diagram, right? Right. And uh, so for intrinsic semiconductor, your formulable will be at the middle. So because number of electrons equal to number of holes, so your formulable will be here, and intrinsic level will also be very close to the formulable, right? EF, EI will be at the middle. So this part I think is clear. Any question here?
Sir, what is EI?
Yeah, okay, I'll come to this point. EI is the intrinsic energy level. So basically, this is the formulable. Means this is the intrinsic energy level, the formulable of an intrinsic semiconductor. Okay, so I'll come to this point later. Okay, so let's. If there is no question, then we'll go forward. So okay. So let me write down these equations again that we have derived. So you've derived n0 equal to nc e to the power minus ec by ef by kt, and p0 is nb e to the minus ef minus ev by kt, right? Okay, so as I told you, for for an intrinsic semiconductor, this EF is equal to EI. EI is the intrinsic level, intrinsic energy level. This is the formulable, right? So of an intrinsic semiconductor. So I could also write this as NC, but this is only valid for an intrinsic semiconductor, right? So this equation you could only write because intrinsic. So intrinsic energy level is the formulable of an intrinsic semiconductor. You could take it like that. So EI minus EV by KT. So from here I could also write from here I could write NC is nothing but N0 e to the power EC minus EI by KT, right? And NV is nothing but E0 e to the power EI minus EV by KT, right? So so now if I put this NC here, right? So this, if I replace this NC here, so it will be N0 e to the power minus EC minus EI divided by KT times e to the power EF minus EC by KT. So EC will cancel. So this will be EF by EI by KT, right? So, oh, sorry. Okay, so here, so you could write N0 equal to Ni. So because, let me write down. So N0 equal to P0 equal to Ni. So you could also do this as Ni here, and B is also Ni, right? So right. So yeah, so you could always write N0 equal to, so this is means this is the same equation, but it is, I mean, it is easier to write down this equation because you already means basically, okay, let me write down first. So if you do the same thing also, you, right? So these are the two equations. So this is just a derivation. So what you have done here, that you know that for intrinsic semiconductor EF equal to EI. So if and N0 equal to P0 equal to Ni. So if you rewrite the expression, so you'll have N0 as Ni times EF minus EI by KT, and P0 is Ni times e to the power EI minus EF by KT, right? So these are easier expressions to remember than this N0 equal to NC e to the minus EC minus EF by KT, because means most of the time we know the intrinsic concentration of any semiconductor, right? We just remember that, right? So NC and NV are difficult to remember. So in that way, so these equations are easier, right? So if you want to find um, if you want to find N0 and P0, then it is better to use this this last two equations, right? Okay. Now, so if I do, okay, so from these two equations here, if I copy these two equations here, right? So you could write F minus EI equal to, yeah. So anyway, so I'll do it later, right? So so for a okay, so I was just thinking whether to write that or not, but basically you could means basically you could also derive another expression. So let me erase this, right? Okay, so your N0 is NC e to the power minus EC minus EF by KT, and P0 is NB e to the power minus EF minus EV by KT. So we know that this is for a intrinsic semiconductor N0 P0 equal to Ni. So we could do also if you divide these two things, NC by NC and B, e to the power minus EC minus EF by KT here, and e to the minus EF minus EV by KT equal to 1. So, from here, right? So, you could also write down e to the minus EC plus EF plus EF minus EV by KT equal to 1. So I told you for intrinsic semiconductor EF equal to EI. So you could write down this NC by NB equal to e to the power EC plus EV by KT plus 2I by KT, right? Right. And here you could, from here you could also write down, so EI equal to EC plus EV by 2, right? So you could simplify this equation, right? So it will be like this. So here means could also write down this as, so in the, we could B is the effect density state effective mass, right? So so if you look at this equation also here, right? If you look at this equation, so this also shows that this part, right? This part is a very small number because ln. So if you look at the effective density of states, effective mass, effective mass of hole and by effective mass of electron, they are not very different. And on top of that, ln times that will be a very small number. So generally, you could, since this is a small number, right? So EI is EC plus EV by 2, right? That's what I was telling. So for intrinsic semiconductor, so so if you look at the energy band diagram, right? So EC and EV, right? And there is another energy level EI. This is again a fictitious energy level, right? So basically, when we're talking about conduction and valence band, there is no energy gap between between EC and EV, right? So like your Fermi level, right? So intrinsic energy level is also a fictitious energy level. This is not a real energy state, right? So this is just for representation, right? And this EI is at the middle of the band gap. So EI is nothing but EC plus EV by 2, and we call it intrinsic energy level, right? We call it intrinsic energy level, right? And this Fermi level, so Fermi level is also at the middle, because for intrinsic semiconductor we also defined Fermi level is also at the middle, right? So let me draw the Fermi level here also, right? Fermi level is also at the middle. So for an intrinsic semiconductor, you could assume that Fermi level and intrinsic level are at the same place, right? And this is nothing but EC plus EV by 2, right? So if I go by to this equation here, right? If EF equal to EI, then your N0 equal to Ni and P0 equal to Ni also for a intrinsic semiconductor, right?
Sir, Fermi level is always in the between bit.
Fermi level for an intrinsic, see what is Fermi level? Fermi level is the probability. So we define, right, the Fermi Dirac statistics, right? Fermi level is the probability of probability is half there, right? And for at absolute zero temperature, right? I mean at any temperature. So Fermi level, see basically conduction valence band. at absolute zero, right? When you're talking about absolute zero temperature, the probability of finding an electron in the valence band is 100% or 1, and probability of finding an electron in the conduction band is 0, right? And the Fermi level is right at the middle, right? Right. So, and the intrinsic level is also we also derived here. So this is again a fictitious level. So EI is also EC plus EB by 2. So for an intrinsic semiconductor, the EF, the Fermi level, and the intrinsic energy level both are the same energy, right? Okay. So this is about intrinsic semiconductor, but means um, so we know what is the intrinsic semiconductor. This is a pure semiconductor crystal. If you take a pure semiconductor crystal without any doping, without any defects, then means then it could not the number of electrons at the room temperature, number of electrons, number of holes will be Ni. And for silicon, we know Ni is around 10 to 10 per centimeter cube, right? So right, so at room temperature for silicon, we have 10 to 10 electrons, or basically it is 1.5 into 10 to 10 number of electrons per centimeter cube in conduction band, and the same number of holes in the valence band. So for a germanium, then we have around 10 to 13 electrons in the conduction band and 10 to 13 holes in the valence band. So again, you see the intrinsic carrier concentration that depends on the temperature, right? So if you go on increasing the temperature, so because electrons will get energy, so they will go from the valence band to the conduction band, and so there will so the number of electrons in the conduction band will increase with temperature. Same time, since the electrons are going from valence band to conduction band, the number of holes in the valence band will also increase, right? So intrinsic carrier concentration. So as you go on temperature, your electron hole concentration is same in conduction and valence band, but the concentration is different. I mean, the number is different, right? So that's the reason your Ni, your intrinsic carrier concentration increases with temperature, right? As you go on increasing temperature, your intrinsic carrier concentration will increase. And absolute zero, there is no electrons, no holes, right? So basically, your Ni means basically there is no electrons, no holes. Right? So there is no electrons in the conduction band, there are no holes in the valence band. Okay, so this is about intrinsic semiconductor, but we we want to change the conductivity of the semiconductor because we want to use it on our devices. So um, we use the extrinsic semiconductor. So when you talk about extrinsic semiconductor, I'll just quickly go through it. So that means the semiconductor is doped, right? So you take an intrinsic semiconductor, you could dope it N-type or P-type, right? So N-type semiconductor is, that means we have basically you have more number of electrons than holes. In intrinsic semiconductor, if you look at intrinsic semiconductor, the number of holes equal to number of electrons equal to number of holes, right? But for extrinsic semiconductor, um, the number of electrons is not equal to number of holes, right? So N0 can be more than P0 or N0 can be less than P0. So based on that, we call it N-type semiconductor, and the other one we call the P-type semiconductor, right? Because number of holes more, so we call it P-type semiconductor, and number of electrons are more, then we have N-type semiconductor. Okay, so so in extrinsic semiconductor, so is I mean is a process semiconductor, right? So this is done mostly by two processes, mostly diffusion or ion implantation, um, and particularly in the modern um, uh, semiconductor processes or modern fabrication process, uh, we use ion implantation. We do not use diffusion process anymore. So basically, what is ion implantation? So basically, ion implantation is we are implanting. So basically, you take a semiconductor. So let's say we take a silicon intrinsic semiconductor, silicon. Then we implant the dopants to that semiconductor, so that basically this is done by this ion implantation process. So basically your ions are accelerated at a high electric field, and they are implanted to the semiconductor, right? So basically what happens, right? Let's say we have a silicon crystal, right? Silicon crystal, the silicon atoms are periodically arranged, right? The moment you do ion implantation, so ion implantation, so basically this periodic structure is broken, right? So basically, let's say um, we have arsenic, right? Let's say we want to dope it n type. So n type dopants are mostly arsenic and phosphorus. So basically we have arsenic ions. So we have gas here. In this stage you see we have ion source. So we create ions here, then these ions are accelerated. So basically let's say arsenic, so arsenic is accelerated, then the is implanted to the semiconductor, right? So basically here you see, if I have my silicon here, so arsenic ions are accelerated and implanted to this silicon. So silicon crystal structure is broken. So but after implantation, so implantation is always followed by a diffusion process. Diffusion process is nothing but you take the implanted semiconductor and heat it, right? So when you give thermal energy, then the ions, I mean the atoms all go to their original position, right? So this is how a extrinsic semiconductor is formed, right? So basically, basically for a extrinsic semiconductor, so let's say I have silicon. Um, so I have silicon atoms which is periodically arranged here, right? So when then when I talk about doping, so what I have done is I have replaced um, some of these atoms by a different atom, right? So basically these are silicon. So this is my silicon atom and this is my arsenic, let's say, right? So what I've done is I have replaced three silicon atoms with arsenic atom, right? So that means I have created defects in the semiconductor, right? The semiconductor is not defect free. Basically, we had silicon atoms periodically arranged. Now it's not periodically arranged. So at some point I have arsenic atom, right? So this is called the doping process. That means we are replacing the silicon atoms with arsenic atoms, right? So if you go on replacing more and more silicon atoms, that means we are increasing the doping of the semiconductor, right? So uh, okay, similarly for p type, we replace the silicon atom with boron, right? So boron are p-type dopants. So we replace the silicon atom with boron. Okay, so I mean, basically, I'll go back. So so basically, yeah, this is the same thing what I have told you, right? So for an n-type n-doped silicon, we are replacing your silicon atom by arsenic or phosphorus, by arsenic or phosphorus. This is pentavalent impurities. And for to have a p-doped silicon, we replace silicon by boron, right? Mostly this is mostly boron, um, right? So so when you replace silicon by boron, so boron is a trivalent impurity, so it becomes p-type silicon, right? So what is really happening is that um, we know that uh, we have a periodic structure of silicon, right? So we started with that. This course we started with the periodic structure of silicon, right? So this periodic structure, right, gives you a EK diagram, right? So basically, if you see this periodic structure will give you a EK diagram, and we know, I mean, now we know the EK diagram. So basically, we know that this is equal to k equal to 0 point, and this is towards the x value, right? Anyway, so this is the bottom of the conduction band, right? So this is my this is my EC, and this is my EB, right? So and I told you many times this EK diagram totally depends on the periodic structure of the atom, right? So if you replace, so for a germanium we'll have a different EK diagram, right? For gallium arsenide we'll have a different EK diagram. Now what we have done is we created defects in the semiconductor, right? So defects in the semiconductor means we have removed some of the silicon atoms, and we replaced those silicon atoms um, with arsenic, right? Let's say this is arsenic, right? Right. So this is a defective semiconductor, right? The moment you create defects, right? So the periodic potential that we're thinking, right? So basically this EK diagram comes from the periodic potential, because electrons is going, I mean, the electrons is moving in a periodic potential. And if you solve the Schrodinger's equation with many body physics, you will get the EK diagram, right? But now the periodic potential changed, because if you remember periodic potential, basically we talked about uh, this kind of periodic potential, right? Uh, right. So then the electron is moving. That means if you solve the Schrodinger equation, you'll get EK diagram. And these are the atoms we are talking, right? So these are the atoms we are talking about, right? Silicon atoms, right? But now some of the silicon atoms are replaced by arsenic, right? That means we broke the periodic structure. Maybe here, let's say we replace this silicon here, silicon by arsenic. So the potential is changed, right? Then let's say this potential is changed, right? But this is no more periodic, right? Because we are randomly introducing dopants. That means the potential will also changing. That means so this is no longer periodic, right? So what will happen here is, so we did not have any defect states between EC and EV, right? So because of these dopants, we'll start creating defect states, right? So basically we'll have extra energy states, and those extra energy states will be in the forbidden gap, right? Because we broke the periodic structure by implanting different atoms, replacing silicon by arsenic. So we'll have now different energy states coming into picture, and these energy states will basically be in the forbidden gap, right? Right. So for a defective semiconductor, uh, the forbidden gap will have also energy states, right? So luckily, uh, for these dopants that we're talking about, right, arsenic, or we're talking about phosphorus, or we're talking about boron, luckily for these dopants, the defect states are created very close to conduction band or very close to valence band, right? So for arsenic, so if you see, okay, for arsenic, um, so if this is my energy band diagram of the silicon, I have my EC and EV, and I did not have any states. But the moment you implant, you replace some of the silicon atoms by arsenic atoms, there are defect states created in the forbidden gap. And these for arsenic, these defect states is very close to conduction band, right? And this is a defect states, right? Keep in mind, when I'm talking about energy level, sorry, intrinsic level or Fermi level, I was always telling you there are fictitious labels, right? But this is not a fictitious label. This is just a real energy state created, right? And this is just right below the conduction band for arsenic, right? Since it is right below the conduction band, and arsenic, so basically the electrons, so because um, yeah, so what will happen, and this energy gap is less than 26 milli electron volt, right? What is 26 milli electron volt? 26 milli electron volt is kT by q at room temperature, right? So if this is less than 26 milli electron volt, so basically what happens at room temperature, electrons from here, lot of electrons uh, can jump to the conduction band, because there this energy state is created very close to the conduction band, right? Since it is very close to conduction band, the electrons from that defect level can go to the conduction band very easily, right? Because it's they are very close to each other, right? And some of the electrons can also go to the valence band, right? So it's not like that all the electrons goes to the conduction band. Some of the electrons also fall back to the valence band, right? So what is happening here, room temperature, I have some N0 here, right? And I have some electrons and some holes in the semiconductor, sorry, in the semiconductor, right? So now, so every defect that I'm creating is creating a defect state, right? So every defect will create a defect state, right? And let's say I replace one silicon atom by arsenic atom, it will create one defect state. I replace 2 silicon atoms by 2 arsenic atoms, then it will create 2 defect states, right? Similarly, if I keep on adding, replacing silicon by arsenic, right? So it will create a lot of defect states, right? And those defect states have electrons, right? Because see, arsenic has 5 valence electrons, right? So basically, these electrons can go because you would think, let's say, you will make extrinsic semiconductor. The moment means because see, in the implantation process, your crystal structure is damaged, right? Right. Then you do the annealing, right? So then when you do annealing, the bonds formation happens. That means the crystal, then the atoms are periodically arranged again, right? But during this periodic arrangement, some of the silicon atoms are replaced by arsenic, right? So when um, arsenic has 5 electrons and silicon has 4 valence electrons, right? So they form covalent bond, 1 electron is free. That means every defect state has 1 free electron, right? So that free electron can easily go to the conduction band because that defect state is very close to the conduction band, right? Right. So similarly, if you have more number of arsenic atoms, you're replacing more number of silicon atoms with arsenic atoms, then more number of electrons will go, right? So basically, now the number of electrons in conduction band is nothing but the how much donors you are adding, right? How many arsenics are you adding, right? So similarly, some of these atoms, right? It's not necessary that every all the electrons from donor level will go to the go to N0, but some of these electrons from the donor level also go to the valence band. The moment they go to the valence band, the number of holes will also reduce, right? Right. So there will be some X here, right? So some reduction of holes in the valence band also, right? So here you see what you have done is by replacing the silicon by arsenic, we have increased the concentration of electrons in the conduction band, right? Right. So that's why we call it an N-type semiconductor. Similarly, for boron somehow creates um, boron somehow creates uh, a band, a defect state, which we call very close to the valence band, right? Since there is a defect state very close to valence band, we call it acceptor states, because now the electrons in the valence band can go to this defect state, right? Because this is very close to valence band, it could go there, right? So the moment these electrons go to the these defect states, then they leave behind holes, right? Leave behind holes, right? So again, um, means some of the electrons from conduction band will also fall back to these defect states, right? Because see, conduction band, there is always interaction between conduction band and valence band, right? Right. So some of the electrons can fall back. So what happens if you increase more and more boron? That means you are having more and more defect states, and then more and more electrons will go from the valence band to the defect states, and it will leave behind holes. Right? So what is happening here is uh, the number of holes was P0 before. Now it is increased, right? So so because the moment the defect state is created, electron go from valence band to this acceptor level, and it leave behind holes, right? So if you see in the equilibrium, that means at room temperature, so number of holes in the valence band has increased, right? And this is called the p-type, right? P-type semiconductor, right? So see, basically basically these defect states are created very close to conduction band or very close to valence band. Otherwise, there is no way can interact, right? So because room temperature these electrons should go from these defect states to conduction band or from valence band to the defect state, right? Uh, okay. So this is how ends. We have more number of electrons in N-type semiconductor and more number of holes in a P-type semiconductor. And I think I have here you see in means these are the defect states where they are created, right? Uh, so in arsenic is created the 49 milli electron volt below below EC, right? and phosphorus is created 44 millielectron volt below EC, and antimony is also a n-type dopant, is very 39 millielectron volt below uh, below EC, right? So these are n-type dopants. Arsenic, phosphorus are more common. I'll come to this reason why. Antimony is not generally used. Similarly, if you see from the p-type dopants, boron it creates a defect set just 45 millielectron volt above EV. Aluminum and gallium, right? So aluminum, galliums are not very, uh, are not used. So mainly boron is used. Uh, so okay. So again, right? So this is the energy states of a single, right? When you replace a silicon by boron or replace silicon by arsenic, it will create a single defect states, right? But if you are creating, let's say, you doped 10 to the power 18 per centimeter cube, right? So let's say your doping is 10 to the 18 per centimeter cube. What do you mean by that, right? So if you see from the silicon crystal structure, so silicon has 5 into 10 to the 22 atoms per centimeter cube, right? So out of this 5 into 10 to the 22 atoms, if you replace 10 to the 18 atoms by arsenic, that means the dopant, this is the doping, right? So we are creating 10 to the power 18 defect states, right? And these 10 to 18 defect states will be very close to the conduction band, right? If you and see, basically we also means discuss, right? So there is an energy state. If there is multiple energy states, then they form a band, right? So what will happen, right? So if you go on increasing the doping, so basically the defect states, they will not be discrete, they will form a band, they will be very close to each other, right? Because see, uh, for phosphorus this is 44 millielectron volt, right? If you create another defect set, this will be very close to 44 millielectron volt, right? Because it cannot be at 44 millielectron volt because they are already at defect set there, right? So similarly, if you go on increasing, so they will slowly form a band, right? If you go on, doping more and more, so this defect, so what will happen is, let's say this is EC and EV. So you have one defect state, ED, but if you go on increasing, then it will form a band, right? Slowly, right? And this band will increase and they will merge with the conduction band, right? And so there we call that conduction band. So basically, in the very high doping case, um, your donor level and the conduction band, actual conduction band of silicon, they will merge, right? That means your conduction band will become, this will become your conduction band, right? So here, right? So that is called band gap narrowing, right? So if you go on doping more and more, your effective band gap, this is the effective band gap of silicon, right? So this will decrease, right? So this process or we call band gap narrowing, right? And band gap narrowing happens at high doping level. Okay. So okay, again, right? So here, okay, so again, so basically, as I told you, so silicon has 5 into 10 to the 22 atoms per centimeter cube, right? So now we are going on replacing those silicon atoms by other atoms, let's say arsenic or boron or phosphorus, right? So, but there is a limit, right? How much silicon atoms you could remove, right? And you could replace by arsenic or phosphorus, right? And this is called something called solid solubility, right? Solid solubility limit, right? So, so you could think of like, let's you take a glass of water, then go on adding sugar to it, right? So there is a limit how much sugar you could add, right? So how much water could take a certain amount of sugar, it cannot take more, right? So similarly, the silicon, when you are doping silicon with arsenic or phosphorus, so silicon can take a certain amount of outside atom, right? uh, right? And this is called the solid solubility limit. and the solid solubility limit of arsenic and phosphorus are much higher than antimony, right? That's the reason antimony, if you see, antimony is creating a defect state very close to conduction band. In that sense, it is really good, right? But antimony, the solid solubility limit is very low. That's the reason antimony is not commonly used, right? Uh, so that's the reason arsenic and phosphorus are commonly used, because silicon can take more number of arsenic and phosphorus, right? Compared to antimony. Uh, Similarly, the solid solubility limit of boron is much higher than aluminum and gallium, right? That's the reason boron is commonly used, because we want more and more doping, right? So silicon should be able to take more and more doping. So that's the reason boron is commonly used, right? So when I talk about solid solubility limit, arsenic, with arsenic, we could have a maximum doping of very close to 10 to 21 per centimeter cube, right? So that means for arsenic, we could replace 10 to 21 atoms by arsenic, right? In case of arsenic doping, right? So, but phosphorus is around 10 to 20, right? Very close to 2 to 3, 10 to 20 per centimeter cube. And boron is also around 10 to 20 per centimeter cube, right? Right. So, so boron means we could not have a boron more than 10 to 20, right? It's very difficult to have very high boron doping, means higher than 10 to 20, right? 10 to 20 is very high doping, right? That means we have replaced already 10 to 20 silicon atoms by boron, but you cannot do more. But arsenic has a very high solid solubility limit. Means that's the reason we could have very high n-type doping compared to p-type, right? All right. So this is about the extrinsic semiconductor, right? So any questions here, any of you?
Sir,
Yes.
sir, in the case when you said that there's a donor level that we get, so whenever the electrons in the donor level, they'll jump to the conduction band. Like if we increase the temperature, there would be holes that would be created. Would there be holes created in the donor level?
Yes, of course. So because this is a iron, right? So basically the arsenic becomes positively ionized. So right? So you have a Nd plus remains there, right? So the moment this is ionization, right? So basically I have a defect states. If the electrons go from this defect states to conduction band, definitely this there is a positive charge in the defect state, right? Defect state becomes positively charged, right? And that's why I call the Nd plus, right? So basically your atom is ionized, right? So basically the electrons it donates and it becomes positively charged ion, right?
So what is the point of doping? Because if we apply any electric field, the flow of the electrons and the hole would be opposite, so they would just cancel each other, no? If we are getting
You're not getting, right? But holes electrons do not move in the same band,
oh, okay.
right?
Yes,
So
sir.
electrons move in the conduction band and holes move in the valence band, right?
Okay, sir.
So there is always an energy difference between them, right?
Okay, sir.
Sir, I had a question regarding ion implantation. So basically in ion implantation, what we are doing is we are removing a silicon atom and in place of it, we are providing a dopant. So that removed silicon, it won't be like, so that removed silicon will also be there in that crystal, no?
Yeah, this silicon, so yeah, you are right. The silicon does not go away or it doesn't vaporize or something. So basically, what happens is, okay, so um, so let's say I have this silicon crystal. Uh, so so these sites we call the interstitial sites, right? Basically, I mean, sorry, substitutional sites. So these are the natural position of atoms, right?
Yes.
But the moment we just remove this silicon, right, and remove, let's say we remove this silicon with arsenic atom here, and but the silicon is still there, right? But silicon is not in the position where it could bond with other silicon atom, right? So this is in a somewhere like a impurity, right? This is not a active impurity, right? So the moment this arsenic replaces silicon there, then arsenic will bond, right? Right. But this silicon, since it is not in the substitutional site, it is most in the interstitial site, somewhere lying between two atoms, right? And it is not active, right? Active means it is not participating in the bonding process, right? Right. So that silicon atom still there, but it is not in the lattice site, right? And since it is not in the lattice site, it will not participate in the bonding.
So, sir, in this case, these atoms will basically create an hindrance, right, for the
Of course,
movement.
because basically because this could move. Actually, they move, and there is a technique we call the gettering in the fabrication. So we just remove this. Yeah, but they are inactive, right? So since these are not charged and they are not active, they are very inactive. But yeah, sometimes they may create issues, so they are removed from the active area of the device, right? By the process we called it gettering, right? So they are removed from the active area from the device. So this silicon still there, but they are inactive, right? See, that's the reason, right? So as I told you, right? So when you implant, right, you bombard your silicon crystal with arsenic ion, right, with a very high energy, right? So arsenic is implanted. So when but the crystal structure is destroyed because high energy ion is coming and bombardments, right? So it removes the silicon from this lattice site, right? So that means we have all this amorphous kind of region, right? So no order, nothing, right? But to make it active, so because to get a proper EK diagram or to get a proper mobility of electrons and holes, we need to rearrange the silicon atoms, right? So that is done by the heating again, right? This is called annealing process, right? So after ion implantation always follows by the annealing, right? So you take this damaged silicon, then you heat it at some temperature, let's say 1000 degrees Celsius. Then again, this the crystalline arrangement happens, right? So the silicon will slowly go to its lattice site, right? Silicon and arsenic, right? So at this stage, when the silicon is moving to the lattice site, the arsenic moves faster than silicon, right? So that's the reason why the dopant, right? So unless you anneal it, right? So means it will not become N-type or P-type, right? Right? To become N-type, the arsenic has to move to the silicon side, right? Similarly, to have P-type, the boron should replace the silicon in the crystal side, lattice side, right? In the substitutional side, right? Right? So, yeah, so that's the reason implantation always follow with annealing, and you have to do proper annealing. You have to heat it for certain time, right? If you cannot heat it for certain time, then it will not be activated, right? Right. So let's say you are putting 10 to 18 arsenic, and you want all those 10 to 18 arsenic to replace silicon in the lattice site, right? Then it will become active. Then you will tell the, okay, this is doped with 10 to 18, and this 10 to 18 arsenic atoms will give 10 to 18 electrons, right, to the conduction band.
Yes, sir. So, and one more thing, like you said, these interstitial silicon atoms are not active. So, like they are
Active means they
normal
are not
silicon.
involved in the bonding, right? So basically, silicon has 4 valence electrons, right? That's the reason it bonds covalently with 4 different silicon atoms, right?
Yes, sir.
So, but if this is not active, that means it is not involved in the bonding process, right?
So, what about the other silicon atom in interstitial state? So, the two atoms in interstitial state might
So,
bond.
so basically what happened is, see, basically also, see, you see, uh, so let's say you doped 10 to 18 and some of the arsenic atoms also could not go to the lattice site, right? So they also stay here, right? Right. So what happens, this arsenic silicon, they form a cluster, and these clusters move from the active area, right? So you will have this cluster formation also. They are inactive clusters, right? So because they are not in the lattice site, so but this arsenic can react with this silicon in the interstitial, and they form some kind of cluster, right? Arsenic silicon cluster, and but still they are inactive, right? They do not participate in the bonding process, right? But you are right, if you have so many defects, right? So many uh, so it is not also good because electrons, when the electrons is moving, they can interact if they're charged, right? Right. But basically what is done is they get actually automatically removed from those active region, right? So they go to the bottom of the semiconductor.
Okay. Yes, sir. Got it.
All right. So any other question?
Sir, I have a question.
Yeah.
Sir, when you were talking about the donor states, sir, you said that ND we have ND donor atoms in that, and they go into the conduction band to give us N naught plus ND. But sir, you also said that some of them also go to the valence band.
Yes.
They
Yes.
so
So
we get
yeah.
X number of holes subtracted. So sir, in the conduction we should get N naught plus ND minus X, right?
Yeah. But this, you see, if ND is 10 to 18 and this X is 10 to 10, right? Let's say 10 to the 11 also, right? Very 11 basically, right? You got my point, right?
Yes, sir.
So I mean 10 to the 18, right? And 10 to the let's say out of this, um, uh, 10 to the 10 goes to the valence band. So and 10 to 18 minus 10 to 10 is almost 10 to 18, right?
Yes, sir.
Right. So but there are 10 to 10 holes, right? Right. If 10 to 10 electrons goes to the valence band, the number of holes can become 0, right?
Yes, sir.
Right. So that's the thing I'm talking about. So, but there is no definitive statements. This is just a theory, right? Some because it's always possible, right? So when you create a defect states, so the electron can not only go from donor state to the conduction band. There is a possibility that some electrons will go to the valence band, because see, electrons always like to move to the lowest energy level, right? And so from this donor, because this is very close to the conduction band, automatically they go to the conduction band, right? But there is some electrons from this donor state can also go to the valence band, right? And but the probability of means, since we have seen that most of the electrons go to the conduction band, experimentally also shown. So probability that this electrons going from donor state to valence band is less, right? Because this is a means the distance between donor state, the energy difference between donor states and valence band is much more than donor states and conduction band, right? So they easily go to the conduction band. But there are some electrons who go to the valence band, and in that process, some of the holes also valence band reduce, right? See this when I was talking about this expression, like N0 and P0 equal to Ni square. This is not only valid for intrinsic semiconductor, right? So this has been proven that this is also valid for extrinsic semiconductor. So the moment, let's say I dope with Nd, right? So then the number of electrons will become N0 plus Nd, and this will be P0, then Ni square. So if this electron is increasing, so there is a hole should decrease. This is law of mass of action, right? So this has been proven that I mean, see, if you it's basically number of electrons become, so we do that, okay, now the electron is Nd and the number of holes is uh, still Ni square by Nd, right? So this is still valid. So that means what happens is, so the holes, in some of the holes, let's say previously it was 10 to 10 number of electrons, electrons increase from 10 to 10 to 10 to 18, right? But here this goes from 10 to 10 to 10 to 2, right? So there is some process, some amount of electrons go from defect states to valence band, and in this way some of the holes also recombine and the number reduce, right? So yeah, but there is no theory, means clearly experimental demonstration that how many electrons go from the defect state to the conduction band and how many electrons go from defect state to the valence band.
Yes, sir.
Okay. Any other question? Yeah, means anyway, so we are already 3 minutes past 12. So I think I'll stop here. We could continue tomorrow. But any question?